Okay, good morning and thank you for joining us for the third day of Leeds Digital Festival. My name's Claire Cox and I work for the technology consultancy Scott Logic here in Leeds. Today I'm joined by my colleague James Leftley, who will be presenting an introduction to resiliency in the cloud. James is a senior developer at Scott Logic, where he's worked for the past 7 years. He's worked across a range of domains, including energy trading, finance and the public sector. Most recently, James has worked on a large microservices solution with strict high availability and security requirements, a Kubernetes platform and a Kafka platform, all built in the cloud. James co-organises the cloud community of practice at Scott Logic and holds certifications from AWS and Azure. If you have a question for James, pop it into the question box and we'll take as many as we can at the end. And if you'd like a copy of today's slides, just send me an email at the end of the webinar and I'd be happy to send them over to you. But without further ado, let me pass you over to James.
Thank you very much, Claire. Good morning, everyone. Thank you so much for joining us this morning. So yeah, I'll be talking about an introduction to resiliency in the cloud. Today we'll be covering 3 main areas. The first will be some foundations. So this being an introduction, we'll define what some resilience is and some associated concepts, look at how you can identify some requirements for resiliency and how you can measure resiliency. We'll then go on to some patterns and approaches, so things that you can do with your workloads in the cloud to help achieve resiliency. And finally, we'll talk about some testing and experimentation, so how you can build confidence in the resiliency of the solutions that you're building in the cloud. So, for the foundations, before talking specifically about resiliency, I wanted to talk a bit about reliability. So, I could define reliability as the ability of a workload to perform its intended function correctly and consistently when it's expected to. And there are lots of different things that will contribute to the reliability of a system and a workload. So the first, resilience, is obviously going to be the topic today, and that's what we'll be focusing on. But I also wanted to draw attention to security, performance, cost and operations. These are things that I'm not really going to go into any depth today. However, it's important to know that they do contribute towards the reliability of a workload. Cost is an interesting one as well, because reliability and resilience certainly come at a cost, both in terms of the financial cost, the time, understanding the kind of the processes involved, and it can also come as a cost to the business if you don't have reliability or resilience. So understanding the requirements and getting the balance right is really important. And with reliability, one of the really strong foundations and underpinnings is putting effort into making sure that the workload does perform and function as expected and try to prevent any issues and problems that come up. However, things can go wrong. This is kind of quite a famous quote from the CTO of Amazon that comes up quite often when talking about reliability and resilience, and that's that everything fails all of the time. So we can put lots of effort into preventing failures, which is important, and we should do that. But despite all of the best efforts we put in, things can still go wrong, and things still do go wrong and will go wrong. So it's important to accept that this is the case, and as well as putting effort into preventing the failures, is knowing that you can observe the failures when they go wrong and being able to react quickly and have solutions to those failures. And these failures could be things like expired certificates, domain names coming up for renewal. It could be a hard drive is corrupted, could be some value in a cache is wrong, it could be a natural disaster, it could be a power cut, it could be a fire in a data center. There's all sorts of different things that can go wrong. Some are much more likely than others, some have different impacts and severities, but these things can and do happen. So what actually is resiliency? So resiliency is the ability of a workload to recover from these failures and continue to function. So we can put effort into trying to understand what failures might happen, and knowing when they do happen, what can we do to try and recover as quickly as possible. So I mentioned a few failures before. These are some of the most common ones that people consider when talking about resiliency. So it could be infrastructure disruption. It could be a hardware failure. It could be that a server stops working. It could be just a temporary glitch, maybe a machine's rebooting. You can have heavy load on a system. If you have increased traffic to a workload, that could start to have impacts on the performance. It could start to slow responses, possibly to an unacceptable level. It might mean that the service is fully saturated and there are no resources left to serve the end users. Could be a misconfiguration. Someone could change a setting. That setting could then lead to a failure, something not working properly. Transient network issues can happen frequently. There are so many different layers now, often to the workloads that we're using. It could be that a load balancer starts to deliver errors. It could be that some requests don't fully get through all of the systems as expected and end up in an error response. Could be a failed deployment. It could be a complicated deployment process. Possibly one step goes wrong. That could lead to an incomplete deployment, for example. That could lead to things not working as expected. Could even be accidental data deletion. There could be things that go wrong. Could be human error. It could be a script is misconfigured. It runs on an incorrect environment and data is deleted. Now, for all of these things, there are definitely things we can do to make them less likely, and there's lots of good practices that we can do to reduce the chance of these issues affecting us, but still sometimes they can. And when talking about resilience and reliability, we often talk about availability as well. So availability can be used both as a measure and an objective. So if we're talking about having a service, we might say that it needs to be available a certain amount of the time. That can be an objective. They can often be also used by the cloud providers themselves. So you might hear that different services have different service level agreements or different SLAs, and that might be a percentage of uptime that you expect. So what do availability numbers look like? Availability will often be referred to kind of in terms of nines. So 2 nines could be 99% availability. So if you have a service or a target for 99%, you can expect just over 3.5 days downtime per year. At the other end of the scale, you might specify something to have 5 nines of reliability. If you've got that objective or that agreement with someone, then an acceptable amount would be just over 5 minutes of downtime a year. So that's quite a significant difference, 5 minutes per year compared to over 3.5 days. And you could have sort of any numbers, but these are some common ones that are commonly used. Typically for the cloud providers, they typically do a lot better than the service level agreements that they have on their services. But this is what you can expect from them. And these numbers are also useful to know if you're defining your own availability targets for your own services. So as well as availability, another couple of common objectives that you might come across with resilience are the recovery point objective, RPO, and recovery time objective, RTO. So RPO defines the maximum duration of data loss that is acceptable during a disaster. So that's essentially the time period for which acceptable data loss happens from an event. So that's often, could be defined as no minutes at all if you can't accept any data loss, or it could be an hour or 4 hours. It can depend a lot on the service. You might have a service that caches user session data. You might have quite a large amount of data loss to be acceptable there because you might be able to kind of recreate that easily. If you're doing something like financial trading, you might have kind of a 0 RPO, where it's really important not to lose any data at all. Then recovery time objective is the maximum time from when the disaster happens to being able to recover the system back to an acceptable state afterwards. So again, this could be a minute, it could be 2 hours, 4 hours, 8 hours. It can depend quite a lot on the type of application. But specifying an availability target, an RPO, and an RTO are quite common objectives and something to consider when defining resiliency requirements. You might also hear of mean time to recover, MTTR, and mean time between failure, MTBF. These are more acronyms and things that can be used to help measure resiliency. These are quite similar to RTO and RPO, but are averaged over multiple events. So mean time to recover is just the average time it would take for a system to recover from failure. And mean time between failures, the average time between failures of a system. So these are things that you can measure, and you can help you identify how resilient your systems are. An approach that you can use if you're dealing with lots of applications or workloads within an organization is you can consider using a tiered approach for defining the resilience of the applications. So here there are 5 tiers, and these are just some examples of the sort of requirements that you might associate with different types. So at the top for tier 0, these are the most critical applications. If these aren't working, it could lead to significant financial loss for the organization. So, financial trading might be an example where you don't want to lose any data at all. If anything goes wrong, you want to be able to recover within a minute as the worst case, and anything more than a few minutes of downtime a year isn't acceptable. And as you kind of going down the different tiers, you might have other customer-facing applications, content streaming. That might not be quite as critical as financial trading, depending if that was the main thing for a business, that might be tier 0. As you go down the tiers, you might consider slightly kind of less important applications, possibly internal tools. You might consider customer applications that don't contribute to as much revenue, perhaps the risks are lower with those. And you might have things in tier 4, might be batch processing, for example. You might be processing monthly financial reports, and those might be something that if they don't work one day, you can rerun them the next day, and that's perfectly acceptable to the business, and you can have these tiers. So when defining different objectives for resiliency, you consider defining some categories and some tiers for their applications. So next I'm going to talk about some patterns and approaches. These are just some common things that you can do to achieve resiliency in the cloud. It's not an exhaustive list of everything. It can obviously be very context dependent and very dependent on the different tiers and your availability requirements, but just give you some idea of some approaches for the infrastructure, some of the common things that you can do in the cloud, as well as some application patterns, so things that you can do with your application code. So here on the right, I've tried to make this as cloud agnostic as possible. I've got a region and availability zone. Those are AWS terms, but all of the main cloud providers have very similar concepts, even if they're named slightly differently. So a region tends to be a geographical location. So an example could be London or Paris or New York, Tokyo. Those are regions. And within a region with the cloud providers, you typically have separate zones or availability zones, and they will be, an availability zone will have one or more data center in it, typically multiple data centers for the cloud provider's redundancy. And if you're deploying different components, you typically can choose an availability zone or a region to deploy them into based on the service. One of the fundamentals for designing this sort of architecture is avoiding a single point of failure. So having more than one of pretty much everything you might have is a good starting point, and distributing those across locations can help achieve the redundancy. That might mean that if there's an issue in a data center and it goes offline, you might still have resources that can perform the same job in other data centers, other availability zones available. So using multiple availability zones within a region, such as London, is a common thing to do. You can also distribute workloads across multiple regions. So you could have the same application running in London, Paris, Tokyo, and New York. That can be really good for performance if you have users distributed around the world, so they're closer to the region, they can have lower latency, but it can be also good from a disaster recovery or resiliency point of view. If you have London becoming unavailable, you might be able to route your users from London to Paris, for example. Whether or not you want to go with a multi-region approach can be very dependent on your requirements. You can imagine if you start to deploy infrastructure in lots of locations, that is typically going to cost more. Again, can depend on your specific requirements, but deploying the architecture across different locations can help with redundancy. Load balancing, that can help enable loose coupling, can also enable scalability of solutions. So having a load balancer can let you distribute traffic to different resources. So here, for example, a load balancer could distribute traffic to different compute resources, such as virtual machines in different availability zones. This means that the traffic can be distributed evenly. It means that if a resource becomes unhealthy, load balancers typically have health checks. It means that we can make sure that the users are only routed to healthy resources so that they get the requests and the functionality we expect. You can also use load balancers internally. Here, there's only kind of a couple of tiers. There's the kind of compute tier, and at the bottom, I'm showing kind of the primary and a couple of replicas are sort of the data tier. You can use load balancers between tiers, which can help with your resiliency and the flexibility internally as well. So load balancing can be good. And if you're using a multi-regional approach, you might be doing load balancing at the DNS level. Finally, you can replicate data. So it's great having redundant resources across different locations. But if a location, for example, becomes unavailable for the system to work as you expect, you'll typically want the data in the other locations as well. So you might have a primary database in one location and replicas in other locations. Here, if the primary database, for example, becomes unavailable, you can fail over to a replica that will have the same data in a different location. Sometimes with the cloud resources, they will be specific to an availability zone. Some resources, however, will be regional. So for example, in AWS, there's S3, which is object storage. That's a regional service, or the sort of standard tier is regional, so that automatically will be across multiple availability zones, and you don't have to manage deploying sort of individual components to different availability zones. So consider using the cloud providers' managed services and some of their regional services as well for resilience. When designing workloads to be resilient, you want to consider segmenting them. So as a general rule of thumb, this means avoiding monoliths and preferring microservice architecture or service-oriented architecture. The idea being that with the monolith, you can't scale different pieces of functionality independently. You can't isolate a failure in one specific piece of functionality to others. So consider microservices and the service-oriented architecture. So we want to consider loosely coupling components. Again, this is a way to isolate failures from one component. You can, for you can, for example, with loosely coupled components, scale them independently, a bit like I mentioned, kind of the microservices architecture. With loosely coupled components, you can also consider some asynchronous architectures. So you might use queuing systems or streaming systems to decouple components, which means that if one component fails, the other components might not necessarily be affected, causing some sort of cascading failure. You can consider degrading gracefully as well. If you've got multiple components in your system, if one component is unhealthy, what would the other component do? That depends on it. Ideally, you want it still to function, even if it's in a degraded manner. Say, for example, you have a checkout page on a website and the user's entering their name and address. You might have some functionality that you can enter a postcode and it will look up the address for the customer. If the address lookup service isn't working, you still want the checkout to work because the user can still manually enter their address, even if it isn't ideal. So that component for the checkout could still work, even though you might just disable the address lookup functionality. So sometimes you might disable non-essential functionality if a component fails. You might be able to return just a static response, which might be better than no response at all. You might possibly even be able to return a cached response if the component isn't working. It can be very context dependent, but in general, consider if a component's dependencies don't function as expected, what will happen. Here are some sort of application patterns that you can consider. So, as I mentioned before, you can have sometimes transient network issues. This could be a server, load balancer, database, DNS query, for example, intermittently not working. These might start to generate error responses. Usually, retrying a failed request on the client side can help. If you're doing this, then particularly at scale, you might want to consider what strategy you're using for the retries. So an issue can happen is that if a component fails and lots of clients start to retry the requests and the component becomes available again, it might be overwhelmed with the number of retried requests. So you can use something like an exponential backoff algorithm, which will progressively use longer intervals for retrying failed requests. You can limit the number of retries. You can also introduce a jitter into the retry. So a jitter is an amount of randomness for when the retries will happen. The idea being that you don't have one big traffic spike where all of the retries are aligned at the same time, but the retries will all happen at slightly different times, which means that the service is less likely to be overwhelmed when it's available again. Request throttling is a mitigation pattern. So this can, if you've got some increased demand, rather than it, say, affecting all of the different clients, if you have some clients which are making lots of requests, you might limit the number of requests they can make in a given time period. So you could set a limit of 10 requests per second, for example. If that's exceeded, then those clients are expected to start to back off their number of requests or try again and limit the request to not overwhelm your services. Circuit breakers. So this is a way you can implement graceful degradation. With this pattern, if you have, say, an external service that you know might not always work, you can use circuit breakers. So if you have a dependency on a service and those requests begin to fail, the circuit breaker can open, and that means that no request will go through to the dependency, and your service can return, say, for example, a static response or a cached response. And in the background, your service is periodically just checking the health of the dependency. When the dependency is available again, the circuit breaker will close and it will allow requests to go back through to the dependency. And finally, timeouts. Often when you're making requests for web services, the clients making the request will have a timeout set. There's usually a default. If these are too high or infinite, it might mean that if a service isn't performing quite as expected, you might start to have lots of connections to that service open, more and more requests are made, that service might become saturated. Failing fast and having appropriate timeouts can be good. It can help avoid that oversaturation of the services. And with complex systems where you have lots of services, you need to consider the timeouts of all of the different ones. An incorrect timeout on one service could then have a cascading effect on lots of others to become overwhelmed. Finally, for some patterns and approaches, is to back up. Backing up data is really important. Identifying the data that needs to be backed up, understanding how it can be reproduced from the sources and how that can go back into where it needs to be for the system to function correctly. Knowing that the backup is secured appropriately, encrypted if it needs to be. Consider, how is the data backed up? Is it an automatic process? Is it a manual process? And if you have these backups in place, are you periodically testing them? If you're not testing them, or you're not trying the process of restoring from a backup, then when it actually comes to a real scenario where you really need to do this, it can be, if it doesn't work, then you can be in a really bad situation where you might not be able to recover the data you need. If you're performing these periodic backups as well, then this can be quite good for measuring your RTO or RPO, the recovery time objective and recovery point objective from earlier. If you have those requirements defined, then backing up and testing those backups can help you understand how you might perform relative to those requirements. So the final section, testing experimentation. So this is all about building confidence in the resiliency of the solutions. So generally for the testing, for resiliency, I think the focus is on end-to-end testing. Unit testing, integration testing can be particularly useful for reliability, just ensuring that an application performs its intended function. Unit testing, integration testing can be useful for resiliency. For example, if you have a script that automates backups, you can use unit testing and integration testing to test that script. But as a general rule, for resiliency, we tend to focus on that end-to-end testing and looking at all of the components of the system together, or certainly focusing on many components within the system. So these are some common sort of types of testing and experimentation that we can do. So load testing, by simulating users making requests to our workloads, we can understand what the limits of the system might be, how they work under high load. We can test the scalability, which can help with the resiliency of the system, can understand the limits when the system might break, what happens at that point, do we recover, what could the impact on the customers be? Having load testing in place is also useful for experimentation, where you want to simulate realistic user load on a system. Fault injection is deliberately injecting faults into our systems to understand if they behave as we expected. There's some overlap with fault injection and chaos engineering. Chaos engineering we'll come on to in a bit more detail, but chaos engineering uses fault injection again to deliberately introduce errors into our systems to understand how they work. We can use playbooks. So when a failure happens, we can go through a playbook to investigate the failure, observe what's happened. We can learn from these failures. Much with post-incident analysis. We've talked about hypothetical failures before, like a data center going offline or a hardware failure. And you can hypothesize about lots of different failures, but if you have an actual incident that's happened, then that's a source of a real failure for you. So analysing that incident, understanding what happened, did we meet the requirements or not, what can we do to improve, was the process good? That's really valuable for building confidence. Finally, game days. This is another thing we'll go into in a bit more detail shortly. This is an approach where we can have a day set aside to run some failures, simulate some failures in the system, and understand how the system, as well as all of the personnel and the processes in the organisation, handle these failures. So chaos engineering and fault injection. These are ways of experimenting with our systems, finding weaknesses and areas for improvement. Chaos engineering was, I think, really popularized by Netflix about 10 years ago. They sort of were documenting publicly on their blogs their move from their on-premise data centers to AWS. And a part of this was they wanted to build confidence that if any of Amazon's infrastructure they were using wasn't going to work properly quite as they expected, was to have failures, that their streaming experience for their customers would still work as expected, or work at an acceptable level. Fault injection is used within chaos engineering, and it is this process of deliberately creating some sort of fault. So the sorts of faults we might consider are simulating errors on APIs. They could be internal errors, throttling errors, and availability errors. You could simulate delays in an API, so the responses are coming back slower than you might expect. You can increase the CPU or memory usage on instances, so not as much CPU or memory might be available as you expect. You can terminate different instances running your applications. You can terminate processes running on those instances. You can even simulate an availability zone being unavailable, or in fact an entire region in a cloud provider being unavailable. And one of Netflix's tools that they released is an open source project, Chaos Monkey. This typically comes up again when people initially think of chaos engineering. Is a tool that Netflix used to terminate different EC2 instances, which are the AWS virtual machines, in their production environment. So, at first people can think this is quite a scary thought of sort of randomly almost terminating different compute resources in a production environment. And that is quite a scary thing. And depending on where you are with the risks of your application and also the maturity of your resilience, that might not be something that you can do. And chaos engineering and deliberately injecting faults can seem like a sort of a scary thing to do. There's sort of a slight difference between the two. So the chaos engineering is generally used for generating new information. So it's about possibly uncovering a failure that possibly you didn't think about, not fully understanding how everything fits together, and generating new information about how your systems work. Fault injection is typically used for one specific condition. So, for example, if a primary database becomes unavailable, will the application automatically switch over to a replica? You might expect that to happen, but you can inject a fault to test those specific conditions. So, chaos engineering experiments. This is from the Principles of Chaos Engineering, which you can look up online. And if you want to run a chaos engineering experiment, these are typically the 4 steps that you might take. So the first is understanding what the normal behavior, the steady state for the system is. So you'll need some form of monitoring metrics in place so you can observe the system and say it's behaving as we expect, this is normal. You'll then want to have a kind of a control group and an experimental group. So a group where you're running this experiment and one where you're not. You want to be considering the scenario that you want to run. So is it a server crashing, hard drive failing, something going wrong? And then you observe the difference between the control group and the experimental group. So you generally want to be running an experiment of something that you think will work. So if, for example, one availability zone becomes unavailable, and you expect your application to continue working, you can observe the control group and the experimental group and see, is that true? Is that the case? Would the customer notice an impact of that happening? If your hypothesis, works, or if everything works as you expect, then you've kind of built confidence in that. If there are any issues, then you can further look into those and look to improve them. And finally, for sort of the testing and experimentation, as I mentioned before, the idea of just randomly terminating some instances or even doing that in a very controlled way in production can be quite scary. And to do that in a controlled way can take significant effort. Something you might want to consider instead, or at least as an earlier stage, is running a game day. So game days have been run as early as the early 2000s, at least, and Amazon have been doing these for a long time. And the idea is that you set a day aside. During that day, you will have an environment that's as close to possible as your production workload running. And during that day, you'll introduce a failure or one or more failures into the system. And you will observe what happens, how the people work, how the systems work, how the processes work. And at the end of the day, you will analyze what happens. So the sort of steps you take for defining a scenario are identifying the workload or the workloads that you want to exercise, that you want to build confidence in, understand all of the people involved with that workload, so development, operations, testing. You want to define the events that you want to practice. So is it an EC2 instance becoming unavailable in AWS, a virtual machine? Is it increased latency between some services, for example? Previous failures are a really good way to focus on. If something's happened before, then that can be quite good to run a game day on to understand how that works. You'll generally want to then, as part of defining the scenario, communicate to all of the people involved that there will be a game day on this date, but you don't want to give them the specific details for the people operating the system of what the failure will be ahead of time. You'll usually identify possibly one person in an operations role who will be running the scenario, and you want to kind of keep them separate so the team operating the service don't have sort of time to specifically prepare beforehand for the particular scenario. You want to make it as realistic to a real incident where you typically won't see it coming until it actually happens. And you'll also want some people to be identified to observe the game day. So these are people who are watching what's happening on the communication tools, what the people are doing, what actions were taken, who aren't actively involved in the process. You'll also need, as part of defining the scenario, to have an environment where this game day can be run. Typically, it might be a non-production environment that you have that's as production-like as possible. And you'll typically want the person or people operating and who will actually be running the scenarios to have some sort of run book in place, preferably with as much automated as possible to simulate the failures and to be able to run those confidently on the day. Also, if you're running a game day, you should be well aware of what actual production systems are doing. So if there are any production incidents, you can stop the game day to deal with the more important production issues. When it comes to running the scenario, you announce that the game day has started. You usually have the people actually introducing the simulated failures or events isolated in some way. Once the game day is started, they will begin to run these events. It's then for everyone else involved to see what happens. Do they observe the system? Does it automatically heal? Are there any other issues? For example, does it need manual intervention? When the game day is finished, you say that it's over. And then once the game day is concluded, you can analyze the day. So you can use root cause analysis, for example, to document what happened. Did the tooling processes, procedures followed all work as expected? Were there issues? What happened? And you can use this as an iterative process to improve the resiliency of the systems, the personnel involved, and all of the processes. So this has been an introduction to resiliency in the cloud. I think that the main takeaways for me are having the mindset that failures are inevitable, to embrace them, to define requirements around them, to measure the performance of systems against resiliency requirements, to consider it when designing and implementing systems, and finally to test and experiment with them to improve the resiliency. So thank you very much for listening. I'm James Leftley. If you have any questions or want to talk after this event, then my email address is there. And Claire, I'll hand back over to you now. Thank you.
That's great. Thank you, James. And yeah, as James just said, if you want to carry on the conversation with James, do get in touch with him. If you're interested in hearing more about our community of practice, cloud community of practice at ScottLogic, feel free to reach out to James. If you'd like a copy of the slides, drop me an email and I'd be happy to send them over. We've got a short survey that will pop up at the end. It'd be really useful if you could take just 1 minute to provide your feedback. And if you're interested in exploring opportunities at ScottLogic, again, you can just check the right box on the survey, and someone will be in touch. But I've been keeping an eye on the Q&A box here. There are a couple of questions that have already come through, but keep getting the questions into us. So let's get going with the Q&A if you're ready there, James.
Yeah, absolutely.
Great stuff. So the first one I've got is, how could you approach considering resiliency requirements when designing a solution?
I'd recommend looking into failure mode analysis or failure modes and effects analysis. So this is a process where you can you start by identifying the possible failures. I'd definitely recommend looking at the cloud providers' documentation around reliability and resilience as a starting point. So one of the first things you can do is identify what failures might happen to the system. For example, as mentioned earlier, infrastructure disruptions, a common one. Then for each component in the system that you're designing, for each of the failures, consider the severity of the failure, the probability of it happening, and also the detectability of the failure. So infrastructure disruption might be quite severe, but it might be a lower probability. And do with your design, is there a way to detect if that failure happens? And from those three factors, you can consider the risk to that component. So have a discussion about each component in the system, looking at those factors, record for each component the risks for those different failures. And once you have the kind of risks associated with each component, you can prioritize based on the risks, which components you might prioritize and for which failures. And then from there, you can look at what mitigations you can put in place, and that would feed into the design and architecture of the system.
Great stuff. I've got one more question here before we wrap up, and that is, could you integrate fault injection testing into a continuous integration / delivery pipeline?
So yes, I think you can definitely integrate fault injection into pipelines. It's much like other end-to-end tests that can quite commonly be in pipelines. So you might simulate a failure to a component from a pipeline. So you could have if you've got an environment that's suitable to you, so you might be able to create one as part of the pipeline for testing purposes. There are tools available. So in AWS, for example, they've fairly recently announced their fault injection simulator that can simulate faults in the environment, and you can observe what happens and have that as part of a pipeline. So you can certainly do that. I think related as well to the kind of continuous integration and delivery approach, there's this idea of continuous resilience. So you might have an environment where you're constantly running different resiliency experiments, you're constantly injecting different faults, and this is a way that you can build confidence sort of continuously. So that is outside of a pipeline, but it is still a continuous approach to understanding the system.
Great stuff. Well, I think that's all we've got time for today. So I just want to thank everyone for joining us today. We will send an email afterwards with a link to the recording if you want to watch it again or share it with a colleague. And thank you to you too, James, for that fantastic webinar. Really appreciate it.
Oh, thank you very much. Yes, thank you, everyone.